Hello and welcome back. And today I'm going to be doing a Unit 4 full review guide for content. Okay, so I'm going to be showing you all the content you need to know for Unit 4 of AP Calculus AB. Now, Unit 4 is quite short with only 7 topics. Topic 4.1 focuses on interpret the meaning of the derivative in context, right? So if you want to work on context problems, context-driven based problems, you need to understand this. The College Board specifies two important ideas. The derivative of a function can be interpreted as the instantaneous rate of change with respect to its independent variable, right? So you're saying it's changing at this rate with respect to whatever input it is, right? You also need to know the unit is just the unit for f divided by the unit for x, right? It's that simple. And here's an example that encapsulates both of those. And this is from the 2021 AP Calculus ABFRQ. It's modified. So it gives you this table and it says the density of a bacteria population in a circular Petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f. And it gives you f of r is milligrams per square centimeter, r is centimeters. And it's saying, question A, suppose f prime of 2.25 is approximately 8. Normally, they'll ask you to approximate it, but let's just say we know it's approximately 8. Using correct units, interpret the meaning of f prime of 2.25. Remember, we need to know it's the instantaneous rate of change of what is f? Well, the milligrams per square centimeter, right? Or sorry, the rate of change, right, in respect to centimeters. So we need to get the units right, and we need to interpret that it's changing at this rate, okay? So what does this mean, right? It means that at a distance of r equals 2.25, right? R equals 2.25 is crucial. We need to say at what instance. From the center of the Petri dish, right? This is all the problem. The density of the bacteria population, which is f of r, right? is increasing, right? Because f prime is positive at a rate of 8 milligrams per square centimeter, right? Proper units. Now, 4.2 talks about rectilinear motion, particle motion, position, velocity, and acceleration, right? So we'll let x of t be a particle or object's position function on a straight line relative to a point P. The velocity of the particle at time t is given by v of t, which is equal to x prime of t. The acceleration is a of t, and it's x double prime of t, which is v prime of t, and the speed is the absolute value of velocity, okay? If velocity is positive, the particle is moving to the right or up. If velocity is negative, it's moving to the left. Also, if you have north, east, southwest, you need to know that too. Um, Now, the particle is speeding up when both v of t and a of t have the same sign, and it's slowing down when v of t and a of t have opposite signs. Also, just a little note, the derivative of the absolute value is just the function over the absolute value. And of course, if you're using chain rule, don't forget to multiply. Um, and that's basically it. However, we're going to do a lot more rectilinear motion when we get to integration, so keep that in mind. Now, I'm going to skip topic 4.3 for now, and I'll get back. It's at the very end. So 4.4 and 4.5 is just related rates. Now I'll give you some steps, right? I won't solve problems here because I already made a unique video dedicated to related rates, but of course, here are just the steps, some tips, right? Now you need to know that you should be able to identify all the variables. Everything that is varying, everything that changes, you need to be able to identify and assign it with a variable. Then you're going to name them, right? And if you have a picture, be sure to write which one is which. Write out what is given, right? If they give you a rate or if they give you a variable at a point in time, write that out. Then you're going to write the equations relating the variables, whether you have to use Pythagorean theorem, similarity, right? Area, volume, whatever it is, as many equations as you can write, write them, okay? Remember, you have to write the variables. Even if they give you a value, don't plug it in yet. Just write it, okay? Implicitly differentiate using chain rule, right? In respect to t, you should already know how to do that. Respect to time, time is the crucial thing, right? dt. Then isolate the rate you are looking for, right? Using algebra. And once you have whatever it is, maybe you're looking for the rate of change of the radius, dr over dt, be sure to, um, once you have that isolated, plug in all the values and rates, and you're done, right? Then you could just find the rate that it's looking for. Topic 4.6, approximating values of a function using local linearity and linearization. We can approximate any function value at a point by using a linear approximation. The formula you might want to remember for MCQs is this, and I'll show you kind of, if you don't want to memorize that, how to get it. So it's basically saying this and this. These are the same thing, right? F of A is here, but it's saying delta X has to be very close to 0 or A has to be very close to X. I'll show you what I'm actually doing here. Let's say we have a function, the square root of X, and it's asking to approximate the square root of 23. We know the square root of 25, right? We know for X equals 25, we know the function's output, right? So what we're gonna do is that we're gonna draw a tangent line to the point 25. Now, we know that if f of x is the square root of x, and then f of 25 is 5, the tangent line to the function at the point is a linear approximation of f, which is stronger, right, for x close to x naught, right? Once, the x gets larger and larger, like farther away from x naught, then it's not as strong of an approximation, or it might be a horrible approximation. But assuming it's close enough, it's a pretty good approximation. So we take the tangent line to the point 25 because we know that, right? And we use our derivative rules to get, it's just this line, right? Point slope form. And then now that we have the equation for the tangent line, um, then we can finally just do this plugging in the value 23, which approximates the square root of 23. We get 4.8 and we're done. So you need to know how to do this. Now for unit 5, when we get to convexity slash concavity, you need to know that if f is concave up, the tangent line underestimates f. And if it's concave down, the tangent line overestimates f. This is part of the interpretations of convexity. Now, topic 4.7 is using L'Hopital's rule for determining limits of indeterminate forms. Now, you need to know the College Board, for some reason, likes to say, oh yeah, the ratio of two functions tends to 0 over 0 or infinity over infinity. Such forms are indeterminate. Other indeterminate forms, maybe your teacher wants to cover it, but it is not examined on the AP test, right? This is L'Hopital's rule. If f and g are differentiable and the limits equal to 0 or positive infinity or negative infinity, then the limit of their ratio is just the limit of the ratio of the derivatives. So if we have an indeterminate form 0 over 0 or infinity over infinity, we could take the derivative of the top divided by the derivative of the denominator. And if it doesn't work the first time, we can keep going and going and going and going until eventually, hopefully, we will get, an answer. And here's a good practice FRQ, right? Straight from College Board, a previous AP exam. It gives you this function, it gives you the graph of f prime, it gives you f of 2 is 1, right? And it tells you f prime consists of two line segments in a semicircle. Crucially, it's asking us to find this limit, okay? Our first idea might just be to, plug it in, but we can't do that yet. So I'll show you how I solved it and how the College Board wants you to solve it. Here is where rigor comes in. The rubric is pretty particular about this. In order to evaluate the limit of the numerator, we're just going to use our rules, right? And obviously we know the limit of minus 3x. So we need to find the limit as x approaches 2 of f of x. Now we know f of 2, but we don't know the limit, right? The limit isn't always equal to the function's value. However, it is equal if and only if f is continuous. That's the definition of continuity. So how do we know f is continuous? It doesn't say that. But we do know that at 2, f prime is defined. So f is differentiable at x equals 2. Therefore, f is continuous at x equals 2. So we have this limit holds. You need to write that out, okay? And now we can write that and say, oh yeah, the ratio of the numerator is 0. The ratio of the denominator, you just plug it in, you get 0. So by L'Hopital's rule, we take the derivative and we get this, right? And now it's a direct substitution. Since f prime is continuous, you should know that the limit is just straightforward, plugging it in, and we get -3. So that's how you do that. So know that you need to, I would personally write out, right, the limit of the numerator and the limit of the denominator separately, so they both go to 0 or positive infinity, and then use L'Hopital's rule. Specify you're using it. Make sure you can get all of points. Topic 4.3, our last one. I skipped it for a reason. It's because really, it's kind of easy. Rates of change in applied context other than motions. And I got this from this guy. I don't want to mispronounce his name. but this is his book. You should go check it out. It's really good. Just search it on AP Calculus AB, straight out of here. In general, if a function is increasing at a certain point, then the sign of its derivative at that point will be positive, okay? It's it doesn't make sense to say a function is increasing at a point, but hopefully you can make some sense of it, right? Even though it's not precise to say it's increasing at a point, right? Or saying if it makes sense to kind of say if it has an upward trend around that point, right? The outputs to the left are less and the outputs to the right are greater, right? Then the sign of the derivative is positive, all right? So if we say h of x is a function representing a height, if h prime is positive, the height is increasing. If h prime is negative, the height is decreasing. If h double prime is positive, the rate at which the height changes, which is h prime, increases. Similarly, the negative, the rate which it changes, decreases. You don't have to use it specifically for height. That's all it's saying. You just need to know what rate of change is in other contexts in motion, right? Maybe water is leaking, related rates. Come on. Come on. If you know how to do related rates, this should be easy. If water is leaking at a rate, you should know what that rate means in context, and you should know it's the derivative. These are all important things that you should be able to interpret, right? And that's why I left 4.3 for the very end, right? So hopefully this helps you in your studying, and Unit 5 will be coming out soon. I'm looking to complete all 8 units. Remember, this is a content review. You cannot passively learn and get a 5 on the AP exam. You need to go out and practice, but this should help you kind of refresh your memory on the concepts. So good luck and keep studying.